In this video, I hope to provide a brief introduction on some of the connections and uses of symmetry as it pertains to solid-state materials. So, symmetry, you can think of this as kind of like a geometric or mathematical and abstract. So the connection to to properties is not necessarily intuitive. It's kind of an abstract connection between these two ideas. But probably the most famous connection between physical sciences and symmetry is Noether's theorem. Noether's theorem says that if your system has some sort of continuous symmetry, that there is going to be some conservation law, some corresponding conservation law. Likewise, so this is an illustrative example that when we can look into the math of symmetry, properties of materials or predictions about materials can be made. And for pertaining to solid state, if you consider the types of symmetries in solid state physics, where you're looking at some periodic lattice, so some square lattice, and you look at the unit cells of these lattices, you might be able to ask yourself, what symmetries does this square lattice have? And you could say that you could apply some rotation to it. You could rotate it 90 degrees and you would still have a square lattice. You could, or a square unit cell. You could apply mirrors at various places. You could do one down the center. You can also do it on the diagonals. So you have a total of 4 mirrors that you can apply, that after applying this mirror, you still have a square lattice. Obviously, there's other types of lattices. For example, if you had some sort of triangular lattice, now your rotation, if you rotated it 90 degrees, you obviously wouldn't have the same shape. This triangle, you need to rotate it. You need to rotate it by 2 pi over 3 for that threefold rotation. You need to rotate it 1/3 the way around the circle in order to return it to its original state. So the idea is that between these, you have different lattices. You have different symmetry operations. So this fact is useful as a classification system. Now that I've provided a brief introduction to some of the reasons that we're interested in these symmetries, I want to nail down a little bit more the specific definition of what is a symmetry. And specifically, a group of symmetry operations. So, I mentioned a few types of operations earlier, like reflections / mirrors and rotations. So one thing that I didn't get when I first started learning about that is like, why do we restrict to these operations? For example, one could imagine, say, you just have some rectangle, doesn't matter, and you define some operation such that you switch point A and point B. You just take these two atoms out of the paper and switch their places. Now, if you did this behind my back and I see the paper after you've done this, I wouldn't be able to tell the difference. So is this a symmetry operation? By the broadest definition, it is, and this is kind of called, in math, this is called a permutation. And this is a really huge group when you're talking about a physical object. If you have a set of points that is like 5 points, you have 5 factorial permutations that you can do. It's the amount of ways that you can arrange it, and doing one swap gets you to a new permutation. But obviously, this is not included in the set of operations that we're allowing. The reason why we do these restrictions, is permutations, that's not really useful when you're talking about any object of like real size because of how fast factorials blow up. But these reflections, mirrors, and rotations, the nice thing about them is they're all linear transformations. So to points in three dimensions, they're represented by matrices that are 3 by 3. And another point is for reflections and rotations, they are distance preserving. What does that mean? That means, take the example of rotating, as the Earth is not rotationally symmetric. Obviously, you can tell the difference between North America and Europe as Earth rotates along its axis. But the idea is when Earth rotates, it doesn't change the distance between State College and Boston, for example. As Earth rotates, the distance between those two cities are preserved. So rotation is a distance preserving action. Finally, the last property of the restrictions of the group of symmetries that we have under our restrictions is the idea that 1 point won't move. I should say at least 1 point doesn't move. So if you look at the rotation of a sphere, obviously all the points along the axis don't move. If you did an inversion where you took, say, every point r to some point negative r, a point at the center, r equals 0, just goes to 0 again. So you have at least one point that doesn't move in this class of symmetries. With the restrictions that we just came up with in mind about, so the distance preserving, the 1 point not moving, rotations, reflections, linear transformations, all of these restrictions in mind, what you actually get when you talk about what are all of the available symmetries of an object is called a group. And this is going to be defined as all available symmetry operations. So one thing to note from a mathematics perspective, this all is really important. This all comes from the idea that in group theory, a group is closed, which means if you compose the elements that are in the group, you stay within the group. So that means if I had some symmetry operation that's a rotation, and then I did some mirror after it, and to keep it consistent with how it's written, you usually read these right to left. So let's say I did the rotation first and then the mirror. This is going to be a member of the group on its own. So let's tidy up some notation, and I think the notation that provides the most insight as to like what these groups are is called the Schoenflies notation. So let's take an example of Schoenflies. So one group in Schoenflies is called C3. And what it describes is an object that has threefold symmetry. So say this triangle where the rotations you have to apply, you have to rotate around the circle, like a third of the circle on each rotation. So let's say you can rotate a third of the way around, so rotate essentially by a 2 pi over 3. But you can also do this twice, right? So if this 1 2 by 3 rotation is part of the group, so is doing that twice, which would look like a 4 pi by 3 rotation. And then finally, you have your 6 pi by 3 rotation, and that's equal to just your 2 pi. But that's just all the way around. That's the same thing as just doing your identity. So the way that you write that down in Schoenflies notation, so that first, all of these rotations have the symbol C, and the subscript 3 to denote that it is a threefold rotation. So you have threefold applied once, see a threefold rotation applied 2 times, and then finally a threefold rotation applied 3 times, and that's just equal to the identity. So now looking at a more complicated group, you would have, say, C3V. So now, in addition to considering the rotations of the group above, we're also going to consider that you're allowed to, say you're allowed to mirror now. And so in addition to the rotations, there's mirrors. So how do you write that out? So C3V. Start the same way with the rotations. So do no rotation or the identity. And then 1 threefold rotation, 2 threefold rotations. And now we're going to talk about these mirrors. These mirrors are represented by the symbol sigma with a V, representing that they are vertical mirrors that are perpendicular to the plane of viewing. So write that as sigma V, sigma prime V, sigma double prime V. Great. And last but not least, for the examples, consider a group D3. So what D3 is D3 is actually an isomorphism of what C3V is, and I'll explain that in a second. But essentially, what if instead we're no longer confining this triangle to things that are happening in the plane? What if instead of, I'm going to use green to denote that it's like a different operation, instead of mirroring it, imagine this green axis is another rotation, except in this case it's a twofold rotation. So the D comes from, D actually means dihedral or two-sided. So I'll write that down. So the D is dihedral or two-sided, which means that, so again, instead of mirroring it, we're just flipping the triangle over. And so everywhere where we had mirror planes before, it's going to be a new axis of rotation. And on these little ends here, these like kind of knobs are symbols that are used to represent that twofold turn. The triangle still has the one axis that's coming out of the page that's a threefold rotation, so that's represented by a triangle. So now if we were to write out the elements of D3, we'd have, as always, you'd have the identity. Doing nothing is always an option. And we have the threefold rotation still, so I'll write those, C3, 1, C3, 2. And now, instead of our sigmas, we have these dihedral these dihedral rotations, or these twofold rotations, they're still represented by the letter C because they are still rotations, but they're twofold now. And there's 3 of them. So I'll write these. You can notice that these are isomorphic. There's a 1-to-1 correspondence between the elements in C3V and D3. So obviously the identities correspond and the threefolds correspond, but the sigmas, so the mirrors, matches the I should color code this the way that I had it down. These sigmas here correspond with the twofold rotations. So that's the kind of definition of isomorphism and why these two symmetry groups are isomorphic to each other.